So this is the first video for chapter 2, and at the end of chapter 1 we went through the different primitive Java types, those 8 types, and contrasted them with Java objects. And so what much of chapter 2 is about is performing manipulations and operations on those primitive types. And as you can see here in our test project here, there's several different test classes I've got with different operators in them. In today's session we're going to concentrate mainly on binary operators, which we're used to in our everyday kind of arithmetic that we do, and unary operators, and several more to get through. Once we've got through all of these, that'll be much of chapter 2 done. And by far the biggest one really is binary operators. They're the most common ones, and they're also the ones with the most rules and exceptions and that kind of thing. So we'll go through it, and the good thing about it is that much of it is fairly intuitive from everyday arithmetic that we do. So I've got this test class, it's called binary operator tester, and I've put some Java doc in it here, explaining a little bit about the background. So here are some of the binary operators, and binary just means, of course, that the operator acts on 2 operands. So equals, that is an example of a binary operator because you have 2 operands either side of the equals sign, so x equals y, for example. And arithmetic binary operations that most people are familiar with, so plus, minus, divide, and the asterisk, which you use for multiplication. Here's one that not everyone will be familiar with. It's like they use the percentage sign, and that's a modulus or remainder. We'll be looking at examples of all these in a minute, but these are the basic binary arithmetic and assignment operators here. And just in the notes I've said here that by convention we use a space to delimit the operators from the operands in a binary expression. So here's an example. We've got int I equals 1 plus 5, and there's a space between each of those. There is a binary operator, and there is a binary operator, and there's a space between all of them. But it also works fine without any spacing or with multiple spacing, as we'll see in a minute, but that's the convention to do it that way. And binary arithmetic operations follow these BODMAS system as taught in schools. So most people are familiar with them. So multiply, divide, and modulus take precedence over plus and minus. So we'll see what that means in a minute. But you can override the natural precedence by the use of brackets. And when priority of operand operators is equal, things are evaluated from left to right. So we'll see that in action in a minute. It's just what we're used to, in everyday arithmetic anyway. Here we have some rules here around arithmetic expressions, rules of promotion. I'll come back to these 4 rules once we get to that part in the demo. But just coming now into the class now, we've got our main method that's going to demo some of these things. As we said, by convention we use a space to delimit things here, which is we got there. That's just the normal convention. We can do it fine without any spaces, still compiles, or even lots of spaces here. But the convention is like that. Java doesn't really mind, even though you'd hopefully never really do something like that. Java is only really concerned with which token follows which other token. It doesn't really mind about white space. So just to show that you can do that, but this is the way we try to do it with binary operators. So to show what we were talking about in terms of precedence, let's just look at an expression here. So we've got 1, 2, 3, 4 binary operators strung together, and then the equals one as well, because the result of that is going to be assigned to an int. So let's see which bits of this get evaluated in which order. I've kind of summarized it below. So the first thing that happens, it will by default go left to right, but it'll take into account precedence of certain operators over others. So the first one is this 2 multiplied by 5 will be evaluated first. So the expression becomes like this. It'll be 10 plus, and then the rest of it all the same. Then what happens is that the 3 multiplied by 4 is evaluated next. This is effectively where we are, because we've already done the 10, the 2 multiplied by 5. 3 multiplied by 4 is done before this 10 plus 3, because multiply takes precedence over add. So what you end up then is 3 times 4 is evaluated, so the expression becomes like this then, 10 plus 12 minus 8. Now they're all just the same precedence because plus and minus have the same precedence, so now it's just evaluated left from right. So 10 plus 22 is 10 plus 12, sorry, is 22, minus 8 is 14. So if we actually just print that out, we should get hopefully a result of 14 in the evaluation of it. There it is, 14, so that's great. And as we mentioned before, bracketing can change that precedence. So down below here, I've got exactly the same sequence of numbers. So we've got 2, 5, 3, 4, 8, 2, 5, 3, 4, 8, and all the same operators. But because we've got bracketing and then nested bracketing, we forced the precedence to be overridden. So as this is fairly intuitive, I won't go through exactly what happens step by step here. I'll allow you to just do that in your own time if you want to, but just what I will do is just print the result of the second one, just to show that it's different from the first one, because the bracketing has forced a change. So it was 14, it's now 48 because of our bracketing. So the modulus one, which is what some people are less familiar with, the percentage sign, it's kind of related to divides. So we've got a few examples here with divide operator and the modulus operator. But what my modulus does, so what? Let's do the first one. 9 divided by 3 there. As we expect, that's going to output 3 when we do it, I hope. It does there. So what 9 modulus 3 does is that does a division too, and it prints out the remainder. Well, 9, so 3 goes into 9 3 times exactly, there's no remainder, so you expect that to output 0 there, and it does. And here 9 modulus 6, well, 6 goes into 9 once with a remainder of 3, so we'll expect that to give us 3 there. This final one is not modulus, this is another division one. This is actually showing a little bit, this isn't really about modulus, this is illustrating a different point. We're saying print 9 divided by 6, and what that actually should be is 1.5, but it only prints 1 because we lose precision there. And the reason it only prints 1 is that if you remember from chapter 1, when you just specify a number like that without having already defined it as a variable type, so you're just putting a number literal straight into an expression there without having defined it as a variable, Java will always treat that as an integer, an int, so as long as it doesn't have a decimal point, in which case Java treats it as a double. But these are being treated as ints, and integer doesn't have a decimal point. So it does 9 divided by 6, which is 1.5, but it has to discard the 0.5 because it doesn't have the space to store it. So you end up with the 1, but you've lost precision there. We'll see more examples of that, and I think we go into more detail in that later in the syllabus. So here we have, just to show some more examples of precedence and the difference between double and int. Here we have some 2 expressions here which are identical. They have exactly the same numbers in them. In the first one, the result is assigned to a double, and the second one to an int. And again, you could follow the same rules that we followed up here to evaluate that. I won't do that now just to save time, but you could do it exactly the same way. All I'll do for now is just print the results of doing those. So one of them is a double and one of them is an int. And there we go, we both get the same answer, we get 25, but on the double we get a 0.0 there because it's got a decimal point. It's got a decimal point in it. So what we now do is we've got another 2 examples down here. So this example here is exactly the same as the example above, but with one difference. We've got a division in here, 4 divided by 3, whereas here it was 4 divided by 2. So 4 divided by 2 divides nicely and gives the answer of 2. So everything is fine there. It's going to be the same for both of those. You don't have anything to deal with after the decimal point. But here, of course, 4 divided by 3 is going to give a decimal. It's going to give 1.333 recurring. So let's just see what the result of evaluating these is. So I'll double result 2 and int result 2. Okay, so in the previous example they both evaluated to 25. In this example they both evaluated 24. But actually we're losing precision here. We're losing precision because in this example we're assigning everything to an integer, and so we can't hold that the 0.333 recurring. So that explains why the integer one resolves to 24. But why does the double one do it? Because after all, we can store decimal information in here. And to explain that, let's fix it first. And we're introducing a new concept here. It's exactly the same as it was before, but we've introduced the word double in brackets. And what we're doing there is we're casting that to a double. We're casting this number 4 actually to a double. And as you'll see in a minute, when you cast one of the numbers to a different data type, it has a knock-on effect on all the others. And just doing that allows us to maintain that precision that we need. I'll run it so you can see the answer. There we go, we have the precision now on there. It won't be clear yet why exactly that's done what it's done, but we'll go into more detail on that in a minute. And to really understand why it's doing it, we want to return to our Java doc at the top and review what we call the promotion rules. Rules of arithmetic promotion. So I'll go through them. They probably seem a bit dry and wordy, but when we look at them, we'll see them in action. If two values have different data types, Java will automatically promote the lower one to the type of the higher one. That's rule 1. And that's why you see this happening here, because you've promoted, you're saying that's now a double. So this 4 gets divided by 3. So Java thinks to itself, we've got a double here, and we've got an int there, we'll promote that to an int then. It'll automatically do it. Then this ends up being added to this. So that gets promoted to double. So a knock-on effect is that everything in this expression ends up getting promoted to double. So you end up preserving that precision, and you get the numbers after the decimal point, and it gets assigned to a double. So nothing gets lost. So that's all because of rule 1. If two values have different data types, Java will promote one of them to the one of most precision, the highest one. So you don't end up losing precision. If one of the values is integral and the other is floating point, Java will promote the integral one to the floating point one. So that's just an extension of 1 really, and we saw it in that example of using a double. If you have an integral number, that's one without a decimal point, and a floating point one, like a double, Java will automatically promote the one without the decimal point to having a decimal point, so that no precision will be lost in subsequent calculations. So it just extends from 1. It's just saying that it's saying that if you have two types together and you're going to be doing manipulations with them, the one of lower precision will get promoted to the one with the higher, to the same type as the one with higher precision. Smaller data types, namely byte, short and char, are first promoted to int any time they're used in an expression. So if you have a short, for example, and Java sees that you're going to be doing expression with it, it automatically promotes it to an int without you doing anything else. So these 3 types, byte, short and char, which we rarely use anyway, automatically go straight to int as soon as Java realizes you're doing manipulations with them. And after all promotion has occurred, this is the last one now, the operands have the same data type because of this promotion, and the resulting value also has the same data type then as all these operands. So, see, as I say, it seems a bit wordy and dry, but we'll see that in action. We already saw it in action here, because what we're saying, when we had it like that, we lost precision if we evaluate that, because everything here is an int, literal, because that's the default numeric Java type. So when you do 4 divided by 3, it should be 1.33, but because they're all ints, the result of doing that's going to be an int too, and you can't have point anything in an int, so it'll just be 1. So you lose the precision, and you end up with this. But by forcing any one of these operands to be a double, that will have the knock-on effect of making all the others. So Java thinks, okay, he's doing 4 divided by 3, and he's promoting that 4 to a double. Therefore, I must promote this 3 to a double. Then other things will get evaluated, and as soon as anything else has to interact with this double that we've just created, the other thing will be promoted to double. So they'll all be promoted to double gradually as you go through this expression, and the result will be a double. And therefore you can assign this to a double type, but you couldn't assign it to a smaller data type. So you couldn't assign it to a float if we do that, because it knows that you've got a double coming here. It's saying, oh no, that's too small to hold the result of doing this. We know you're going to get a double back here. So that kind of illustrates all 4 of those rules. So moving down here to some examples of things that don't compile. They kind of tie into the rules we just looked at, but they also tie into what we talked about in chapter 1. So none of these compile here. So what we're saying here, we're saying that 1.0 cannot be assigned to an int a. If you remember that when Java sees an expression, it kind of compiles all the tokens individually before then looking at the line as one. So it sees that you're using a decimal point here in a number, and it says, oh right, there's a number there with a decimal point, make that a double. Then you'll try to assign it to an int, and the compiler says, oh no, you can't do that, here's a double, you can't assign it to an int, it's too small. So the same principle applies here, because you've got an int here, that's the default type of a literal number without a decimal point, and you're trying to assign it to a short, which is too small for it. Here you force that to be a float by the use of the f, and you can't therefore assign it to an int. And here you can't assign this number to a long. In fact, it hasn't even got that far. It's a literal number, and it tries to assign it to an int because that's the default type of a non-decimal number. But because it's too large, it can't even do that. So it doesn't even get as far as assigning it to this long in the first place. So below here, if we comment that out again, we've got examples that do compile. So there we go, that's the same ones as above, and they've all been corrected by casting here. So this that would be a double, but you cast it to an int. That would be an int, but you cast it to a short. That would be a floating point number, but you cast it to an int. And here we use this L. If you remember the L from chapter 1, that's how you tell Java that this is actually a long. You could cast it or use the L. So casting is something that will come in a lot later on in the course, and you more often see it with objects than primitives. But this just illustrates that you can use casting, but you should use it with caution, because you can very easily lose precision with it, as we'll see in a minute. There's the principle of overflow. Before we look at that, we'll just look at another expression here. We've got a short, a float, and a double, and this expression here demonstrates all 4 of those rules. So this short, straight away, Java will say, okay, I've got a short here, it's being involved in an arithmetic expression, promote it to an int. So that's one of those rules. Then this short, what will be an int, it gets multiplied with a decimal type, a float. So Java immediately promotes this int to a float. Then what happens, this will be evaluated, and it'll still be a float, but the result of this will be divided by this double. So Java will promote that to a double, and then assign the result there to a double. So it kind of illustrates all those rules. You can't do this, therefore. You can't assign that to a float, because the result of doing all this, of manipulating all these doubles, these will all be doubles eventually, will itself be a double which can't be assigned to a float. So it's just another illustration of it. So here we have an example of a short. This demonstrates the idea of overflow again. So this short can't be assigned this number because it's too big for it. So what we can do instead, we can cast it. So here we are, casting again. We're getting used to casting. It might seem like that solves the problem, but it doesn't, because if you print that now, let's see what s equals, prints that down here, the number is 20678. So what we're trying to say is give this value to variable s, and what we end up is this. So 20678 does not equal that. It's basically a nonsense number for us, and what we've done by casting is we've given ourselves some nonsense data. So while you can cast, it's not always advisable to do it, because what happens is that the principle of overflow kicks in. It will try to assign this number to a short, and it will get to the end of the available slots on that short in memory, and then it'll simply start again at the beginning. So it'll almost like reset itself to 0 and start filling again, and then go around and start filling again until it eventually runs out of numbers that you're trying to assign, and you'll end up with the result here, but it may be completely meaningless. So casting happens implicitly in certain cases. In other words, you don't have to tell Java to do it; it'll do it automatically. So you should always be aware when you're doing explicit casting like this, because you're telling Java to act against its instincts. You're telling it, look, I know that you don't want me to treat that as a short, but I'm telling you to treat it as a short. So Java's got no choice but to obey you. It thinks, okay, well, you say you know what you're doing, I'll allow you to do it, but it should be done with caution. Here we have an example which shows one of those rules of promotion above. So we have two short types here, E and F, and we're trying to do E multiplied by F and assign it to G. Now they're shorts, and this is a short, so until we learn those rules of promotion, that looks like it should work. But if you remember, anything lower than an int automatically gets promoted to an int. So this gets promoted to an int, this gets promoted to an int, it gets resolved, and the result is an int. So you can't therefore assign it to a short. You can get around it using a cast like that, but again, it's not advisable. And that won't work if you just do one of the things. So what you've done there, you've cast that as a short, but as soon as it gets involved with this one again, multiplication here, it gets promoted to an int again. So it starts as a short, Java promotes it to an int, you cast it to a short, then Java promotes it to an int again. So if you're going to do that, you have to capture the whole lot like that. There we go, like that. And of course it's preferable, rather than doing that, it's much preferable just to assign it to an int in the first place. But just to let you know, you can do that, but you're liable to lose precision, or it's more of a risk. Plus it doesn't look great to do that either, really. Just to show that you can, here's just a standard method local variable declaration there, and here's another one. So this one is just showing that you can do like a chained assignment. So you're saying my int 2 is equal to the value of my int, which is that, and while you're at it, change the value of my int to 2, so they both end up being 2. Just bear in mind that you can't do that to a newly created int, so you can't do that where you're declaring that int right there. You can't do that. You can only do this with an int that's already been declared. So combine that. Right, so now in my notes it tells me to look at unary operators, then return here where we've got a few examples of just combining the two together. So let's look at our unary operator tester. All right, Again, I've got some Java doc in here, which hopefully will be useful to you, especially as this project is saved into a Git repository, so you have access to all these Java docs and notes and things. But here are the set of unary operators. There's basically 5 of them, and again, a couple of them we're already quite familiar with, like the plus and negative. Plus in front of something will always make it positive. Negative in front of something will reverse the sign, so it will make something that's already positive negative, or something that's already negative positive. These two, plus plus and minus minus, they're used on numeric types, and they increment or decrement the value by 1. And these can be pre or post. What that means will be explained later on. So these 4 are all work on numeric types. So and this one works on a Boolean type. This is an exclamation mark. It's like it's called the negation operator. What it does, it takes something that evaluates to a Boolean, and it reverses that. So if something evaluates to true, it will turn it false. If something evaluates to false, it will turn it true. And just to say again, that these increment and decrement operators, they can be in pre-format, where they come before the variable. So the variables y and x here, they come before it, or they can become after it, post operators. And this is significant because if these are involved in a large expression, when we use the pre-increment expressions, the variable gets incremented before it's involved in the expression. But when it's in the post form, the expression will evaluate, and then it will be incremented or decremented. We'll see it in action in a minute, so it'll become more clear. With unary operators, by convention, as opposed to binary operators, we don't use a space between them, so that they come directly next to the variable name, like that. And we'll see that in a second. Here we actually have our test class, our main method, and we've got int I here, and here we're using the post increment operator on it, I++. So we don't have a space in there by convention. That's normally how we do it, straight next to the variable name. But as before, it does work fine with a space, or even if you want to, lots of spaces. Not that you'd ever want to do that, but it works. But this is the convention, to do it directly against the variable on which it operates. So let's see them in action. Well, the positive operator, so is implicitly there anyway. So if we do that, we're saying int positive int equals 1. We can say use it there to make it positive, but it's there anyway by default if we do a literal type. So positive operator doesn't have to be used in this context, but it can be used if you have, if you might have a variable and you want to make absolutely sure that it's positive. You could just use that operator and it'll make it positive. A negative operator here, it will just check. So we're saying negative int here equals minus positive int, so it'll take the value of positive int and it will reverse the sign on it. So positive int will be 1, negative int will be -1. So negated Boolean. So here we're saying false, and we're saying negate that. So in other words, turn it to true. So let's do some system acts just to show these in action. So positive int is that, so we're expecting it to print out to 1, and negative int is that, so we're expecting it to be -1. Let's just do those two first. I printed out the wrong, I used the wrong class. It's the unary one now. Let's do that again. There we go. 1 and -1. Now let's have a look at the increment and decrement operators. So here we're saying positive int, which we know is 1 at the moment. We're saying do a post increment on it. So what happens is it says, okay, I know you want me to change the value of this to 2, but you want me to do it after it's used in this expression. So it'll use 1 for this expression, and then it will increment it to 2. So it'll print 1, but the value behind the scenes afterwards, ready for the next one, is 2. Then what we do is we do a pre-increment on the same variable. So the value is 2, we pre-increment it so it goes to 3, and then the expression is evaluated. Then we do the very, very similar thing here with the negative int. So we do a post-decrement. So it starts as -1 here, it starts as -1, and we do a post-negative decrement, so it uses -1 here, but behind the scenes it's keeping it as -2. Then we do a pre-decrement on it, so it becomes from -2 to -3. So we're expecting these to print out as, here we go, so this was the post incremented int, it's 1, and then it increments it to 2. Pre-incremented, it increments it to 3, then it prints it, and exactly the same thing for the negative ones. So that just shows how the pre and the post increment act differently. So here's the Boolean one in action as well. So negated Boolean, so we were saying it's not false, and not false is true. So let's try and see if that works out like that. There it is. So that one worked fine. And unary operators, so we're going to see them now, unary and binary in the same expression. And the main rule to remember is that unary operators have precedence over binary operators. So if you see the whole lot of them together, as we have here, because we've got, there's a unary, and there is a binary, and there's a unary, there's a binary. The unary ones have precedence, but you have to take into account the post and pre-decrement and increment operators when you do it, because it might not appear that they've worked, but they have really. So in this example, we're saying short 8 and byte 4 are literally 8 and 4, and here we're going to divide them. So 8 divided by 4 is 2, but there's an increment operator here and a decrement operator, and they have precedence over this binary operator divides. But because they're both post, that will happen after the expression is evaluated. So this 8 will become 9, a 4 will become 3, but they'll be used in the expression as they were before. So let's just do that to prove it. So there we go with its 2. If we reset them to 8 and 4 again and use the pre-increment and decrement operators, this time that will get changed to 9, and that will get changed to 3, and then the division will occur. So we're expecting this to be 3 now. And there it is. So the final thing to do in this video really is to go back to our binary operator tester and just see some examples of some more examples of unary and binary on the same line here. So here we have an example of a short being initialized to 3, and we've got this big expression here where we're attempting to combine these unary and operators here and binary operators here, but this one doesn't compile, and really this just ties into the reasons that we gave before about promotion. As soon as you start involving shorts in arithmetic, they get promoted to ints, so you can't therefore assign it to a short. The same thing can work if you cast it to a short, but as we said before, it'd be much better just to use an int in the first place. Then you don't get in, need these messy like constructions. But we'll go ahead with this anyway, and we'll, as we did before, we'll just look at this and go step by step what's going to happen here. So remember, it's going to evaluate left to right. Unary have precedence over binary, and within binary, multiply and division have precedence over plus. So let's just do it and see how we get on. So the first thing it's going to evaluate is this. It's a pre-decrement, pre-increment operator. So what's going to happen is that this 3 is going to be incremented to 4 and then return to the expression. So that will, in the expression, appear as 4. There it is. This is step 1. All the rest of it's the same. So then what's going to happen is this will get evaluated. This will decrement it to 3 again, but as it does it in a post way, it'll be 4 that's used in the expression, so that is 4 there. But here we're saying behind the scenes the value of x is now 3, but it gets returned there before it gets decremented to 3. And here, then the next thing to get considered is the next unary operator here, where we have a pre-decrement. So the value is 3, it gets decremented again to 2 and put into the expression. So the expression at this point is like that. Then we're only left with binary operators now, and they'll go left to right and in order of precedence. So this one will go first, the 4 multiplied by 5, which is 20. So you'll end up with this, 20 divided by 4 plus 2. Then this will be evaluated, 20 divided by 4, which is 5. 5 plus 2, which is 7. So let's print that out. Binary again. Let's print that out, and that should give us the answer of 7, which it does. So what I'd say is that if you clearly understood that example step by step, you're never likely to get one that difficult or nasty in the exam. You might get something close to that, but that will probably be the limit of the nastiness of them. If you understand that example fine, and the precedence and the order and everything, and the other examples we've used here, like this, like his, you should be fine for the exam, really. That kind of shows all those rules of promotion and precedence and everything there. The final thing to mention, really, is that the plus operator, when used with strings, serves to concatenate them, so it has a different effect. Everything we've done so far, talking about plus operator, has been talking about numeric types, but if you use them with strings, it's a concatenator. And I think there's a large section of one of the chapters, I think it's 3, where we talk all about strings and the methods on strings, how to manipulate strings, how you keep a string pool, that kind of thing, assigning strings, and the immutability of strings. It's a very, very core Java class, string is, and concatenation of strings, that kind of thing. But for now, just as a taster, we'll show that if you use plus with strings, it concatenates them. So here we have another expression here. We've got 4 different strings here. Part 1 plus comma plus space plus part 2, which is that. So what that's going to do is just going to string them together and concatenate them, and you end up with this, part 1, part 2. So the plus operator on strings serves to concatenate them, and acts to concatenate them. So that is the end of video 1 of chapter 2.